Welcome to my talk. My name is John Lakos. I work at Bloomberg. I'm active with the Standards Committee. Been there for a while. I'm a voting member. I've written a few books. This is one of them. This is another one coming up. Both of these are architecture books. And I'm not going to be talking about architecture today for once. I'm going to be talking about modern C++. And I know about modern C++ because someone very high up in the Bloomberg echelon said, please write a paper about what C++ 11 is somewhere around 2011. And I had no idea. So I couldn't really speak to that. And after a while, we got a lot of people from all over the world to sort of help me learn modern C++. Here are some of them. Here's some more of them. Yet more of them. And now we have this book, somewhere here, I have to find it, which is called Embracing Modern C++ Safely. And that was finished at the end of last year. And it's just a little book. It's got about 1,375 pages in it. And it describes 11 and 14 from the point of view of somebody who knows C++ 03 very, very well, but really just is a little intimidated by this modern stuff. So needed to learn it. And one of the best ways to learn it is to have a lot of experts explain it to you and say, I don't understand enough times until you actually do. Then write it down and get other people to read it and understand it. And then when you're finally done, you have this book. No problem at all. So that almost killed me. Really. So anyway, I'm going to try to give you a flavor for the book, and then I'm going to pick two topics that are related, that are in chapters 2 and 3, and you'll understand what that means in just a second. If I'm going too fast, it's, raise your hand if there's a question to clarify, and there'll be, sort of philosophical debates and arguments at the end. But all I'm trying to do is just get through to the point where we have time to do that. So if something is not clear, raise your hand. I might not even be able to answer the question because this stuff is really pretty involved and hard, and it changes from 11 to 14 to 17 to 20. It's just all over the place. So please forgive me. I'm going to do the best I can because I'm new at this. All right, so embracing modern C++ safely is the first thing we're going to talk about. We're going to talk about the noexcept operator. Then we're going to talk about the noexcept specifier. Colors are relevant. Red is bad. And then we're going to talk about the conclusion. All righty. So here's the introduction, embracing modern C++ safely. You've seen it. It looks like this. What do we mean by safely? So it's interesting that the term safe is not what you might think it means. It's not from your own personal point of view. It's from the point of view of a large corporation like Bloomberg, where we're introducing something into an ecosystem where if you put it in, is it going to cost the company money because you did it? And so chapter 1 features probably won't cost the company any money. Chapter 2 features, you might want to just have some training courses, maybe mention a few things, maybe encourage people to read a book or something. And chapter 3 features are very interesting because there's nothing unsafe about them unless you use them. Then they become a little unsafe. So I'm suggesting that if you know what you're doing, if you really know what you're doing, really know what you're doing, the chapter 3 features can be very valuable. If you don't know what you're doing, odds are you will cause harm. You will do something you didn't intend to do. You will confuse everything out of everybody, and you can actually stop people from being productive. For people who don't understand these features, they wind up doing things with them that just are highly non-intuitive. So I'll explain a little bit more about that as we get into this. So chapter 1, safe features have all of the features sections have feature chapters have 2 sections, the 11 and the 14 versions. So chapter 1 are safe features 11 and 14. Chapter 2 is again 11 and 14, and then chapter 3 is 11 and 14. This makes sense. Now, there are only 3 important chapters in the book. The intent is that when 17 comes along, we'll have a 3rd section of the 11, 14, and 17. And when I say it comes along, it's already here, but we haven't had a chance to use it enough for me to know what I'm talking about. So in 3 years or so, maybe we'll have another edition of this book, and we'll have a 3rd thing. How we're going to fit it into 1 volume, I don't know. But anyway. So each feature has the same format, short title, description, use cases, potential pitfalls, and annoyances. And everything looks the same. And one thing that's nice about this uniformity is you know where to go to find what you need. And one of the suggestions is if you're about to use a Chapter 3 feature, please go look at the pitfalls, please, because now, or look at the use cases and figure out, is what I'm doing something like one of these use cases? If you see it in the pitfalls section, maybe not such a good idea. If you see it in the use cases section, maybe it is a good idea. All right, so moving on, the noexcept operator. So short title, noexcept operator. Long title, asking if an expression cannot throw. Controlling sentence. One of the things that's really important is each feature section has a sentence like this that costs a tremendous amount of aggravation to get right. You want to say something in one sentence, like in the elevator, that says, here's what it does. Using the noexcept operator keyword in its operator form affords a standard programmatic means of querying at compile time whether a given expression, typically involving a function call, can be relied upon never to emit a C++ exception. You see how much time that took to get right? It's crazy. But that's the story. That's what it is. So with that, we have an idea. So what's the description? So the primary purpose is to improve algorithmic performance in generic code. That's really what it's there for. Some operations can be particularly expensive, and if you can avoid them, that's a great thing. So the noexcept operator provides precisely that information at compile time. So this, not to be confused with the Chapter 3 feature, which is the noexcept specifier. Okay, so abstract illustration, we have run algorithm. We say if it's noexcept, we can do something faster. Otherwise, we do something slower. Okay. Conservative behavior. What do I mean by conservative? The compiler is not going to think too hard about this. If there's a possibility that it might, in some circumstance, even if we know it wouldn't, if the compiler thinks it might throw, then that's it. So no except of this, that doesn't throw. What about this one? You see that's actually not no except because there's a throw in there. Now what's interesting is that's also going to report that it's not no except, even though you can look at it and go, wait a minute, it's going to do the other one. No, if there's a throw expression in the thing, then it throws. So this is what we mean by conservative behavior. Now this one's okay, except that there's a bug. So one of the things we learned in this book is compilers have bugs. They have a lot of bugs, lot of bugs. And it's shocking. But the thing is, when you're using it in the way that everybody uses it, they don't have bugs. But when you actually ask the question, what does this do? And then you write test drivers to see what it does, they all do interesting things at the edges. So we learned a lot about that. And unfortunately, anyway, in C++ 17, of course, we don't have to put the quotes. Now, you'll notice throughout this presentation that there are a lot of C++ 11 features that are not this feature that we could have used, but we don't use them. Why? Because each feature is designed to be something that you can pick up and learn if you have a solid C++ 03 background. So yes, I could have left the quotes off, but I didn't on purpose, just saying. So you understand that we don't do things that are surprising. Only the declaration matters. So this is an interesting thing. The compiler doesn't care what the function actually does when it's looking to see if a function is no except. It's interested in what it says it is. So here are some examples of that. And you can see static assert is an exception, by the way. We use static assert so much throughout the book that we just say, look, static assert, very important thing. This is how we write compile time test drivers. So we just put those things out there to say, this is what we expect, this is what we expect, this is what we expect. And so you'll notice that it's the no except that governs whether it's no except. It's not whether it actually throws. Does that make sense? That's a design feature. That's important. This bottom one might produce a warning. G will always call terminate, okay. Compound expressions. When we have more than one expression, we can have it in a number of ways. So here's an example of two functions, and now we've got f1 plus f2, okay. no except true, but the rest are no except false. So those are all the 4 combinations with an operation. Now we have composition, okay? And here's another one. Same thing. See, even with the conditional operator. So you get the idea, right? You got, if this might throw or this might throw, then and that's it. Okay. Even this case, note G is never called. Okay. All right, what do we have here? Okay, so this is a struct. It has only built-in stuff. And so the default constructor, the copy constructor, the equals assignment operator, copy assignment. Now we'll look at move. And so all of these things are no except true by default because this is a built-in thing. All right, but the destructor, yes, all good. Okay, just want to make sure. All right, now, user-provided special member functions. This is an empty class, this is an empty base class. If you state the thing explicitly, then it's no except false. That's what it is by default. The interesting one is the destructor, which even though you put it in there, is no except true. That's a special case, and it was necessary because of the introduction of all of this, the compiler doing all the work for you. When you went from a C++03 class that didn't have any opportunity to put moves in, this seemed to be the best way to go. So this was an engineering decision in terms of migration. And explicitly defaulting member functions get you back to where you were. So if you have these things and then you name them and you default them, then we're back to no except true, including the destructor. This is a really fast tour of this stuff. The nice thing about the book is you can go a little slower, digest it, take a break. This is kind of quick, and this is an empty class, keep this in mind. Now, if you have a derived class, so D is derived from A, all special member functions are no except true, and here, this is not no except, not no except, not no except, not no except, but this one, of course, is no except. So, applying the no except operator to move expressions. So here's, if no except move of this thing, then you can assume no exceptions will be thrown, otherwise do this. And here's another one that says, either it works or don't compile. So those are 2 ways to use the no except operator, right? Some things can just limit what you can do. You can't do this because it doesn't support it. Okay. So applying the no except operator to move expressions. We'll add a move constructor. And I'm using this throw. Throw is a throwback to, the old days. And we're going to use that because it's a fine symbol to say no except. This is was equivalent to saying no except. And so now, no throw. Any keyword, could have used any keyword, but we chose to reuse no except. So we have a no except operator and a no except specifier. Not sure that was the best idea, but all right. So anyway, so this is passing an object by L value reference. This is passing an object by R value reference. Hold that thought. And here's a test function. The compiler will request a move automatically because this thing is a PR value. If you're not familiar with value categories, join the club. There are many people that are not familiar with them. I was not familiar with them. Sadly, now I'm familiar with them. And this will move automatically. This also returns a PR value, and that will move automatically. This will not move automatically. I bet we all knew that. This is right here. We're about to be out of the function, so will that move automatically? People are saying no. Well, they're right. People are right. No, that will not move automatically. So what you have to do is you have to use this move utility. And if you use this move utility, the compiler will now try to move the first one, and it'll try to move the second one. What do we mean by move? You know what we really mean is we're going to cast it to a different value category, and then the compiler will be free to say, you just told me that you're not using that. All right, thank you, I'll take it. Right? That's all it means. Fancy move, nothing moves, there's no compile time, no runtime action going on. It's simply giving permission to the compiler to assume that you're not using it. And if you moved it and you were using it, it's on you. All right. Where are we? All right, noexcept. So here's a struct C, and it has all of its good copy operations from C++03, but it doesn't have move operations. So if I do this, it invokes the copy constructor. This invokes the copy constructor, because there's no move operation. It said, you're free to go ahead and move this, but there's nothing, I hear you, but that's all I got. So we got that. This invokes C's copy constructor. This invokes C's copy constructor, because there isn't anything else to do. All right. So now, we declare one of these, declares only a noexcept false copy constructor. So if I try to move this, is it noexcept? The answer is no, it's not, because the copy constructor is not declared noexcept, and that's what's getting called. So S2 is like S1, is not declared with an explicit throw, and so again, and you have that, and then now we have a copy constructor only, but it's decorated with throw. And now, yes, we can move it, because the copy constructor is as good as a move constructor, and if the copy constructor doesn't throw, then this is true. So if this is interesting to you and you're saying, gee, that's a little twisted, I agree, but it does make some sort of sense, because what we're really asking is, can I copy this thing and have it not throw? Or can I give you permission to move it, and can something as good as a move happen, and will it not throw? That's what happens. So it's a good thing. Anyway. Now, keep in mind that stood unexpected and all dynamic exception specifications, throw becomes are gone, and in 20, even throw goes away. So everything that I was showing you here is not valid C++ 20 code if you see the word throw in it. Nonetheless, I think it makes a better presentation for people who've never seen noexcept, to at least they might possibly know what throw means. But anyway, okay. So we're gonna get rid of that throw and put noexcept there. But that's noexcept is that throw for all intents and purposes. All right. Use cases. We're going to look at pushback. I felt bored one day, so I decided I would actually try to explain what pushback does in clear terms. Took more than a day. Move operations can be significantly faster, especially when we're getting rid of memory allocation. That's one of my other fun topics, is memory allocation. So let's take a look. This is all, I don't want to just read the slide. I'll let you read that, save my voice for something that's useful. Pablo, who's sitting right here, actually demonstrated that for some situations, it's really much better to copy a small amount of data over, especially if you're going to be accessing it very often. So if I've got something here and all I'm going to do is move it, but I'm never going to use it, move might be faster. But if you're going to access that thing that you moved 2, 3 times, it might just be better to copy it, especially if it's just raw data, especially if you're talking about a block of elements. Just bit-blit it over and then use it. So keep this in mind. There is a paper out there to read, and you can see exactly when, where, and how, but it's worth noting. So what's the strong exception safety guarantee? I'm sure everybody's heard this many times, but anyway, it's the state the state, not just the value, but the state of the object remains the same. So something like capacity would also be preserved in theory. Interestingly, there's some differences between 03 and 11. We'll see that later in the talk. In particular, inserting an element at the end of a vector has the strong guarantee. So vector insert or vector pushback, if you put something at the end, it is not going to throw, or it's going to stay in the same state that it was. That's what that means. And my own personal opinion is that was a mistake to give that strong guarantee, because we had to do all kinds of crazy things to keep that promise when very, very few people use it. But we'll talk about that later too. So here's a struct, and I'm making a really fussy type. What it's going to do is it's going to throw on the third copy, just so we can see how annoying things can be. And so this is what it looks like. So there's a static counter. There's an ID that says the unique identifier for this copied object. And there's some things here, like when you copy it, it increments. And we start with 1. And when the number of copies gets to 3 and I try to copy again, I'm going to throw. Make sense? This is a standard testing technique, by the way. If you want to make sure that your code is exception safe, you create a test case and then you test it. When the first time it allocates, it throws. Second time it allocates, it throws. The third time it allocates, it throws, and so on and forth until the operation completes. And then you've used what we call orthogonal perturbation. You've tested a different dimension all along the number of exceptions, places that might be thrown until you actually complete the operation. This is something that Dave Abrahams came up with and published around the same time as I was using it at Bloomberg, but I never published it. I'm actually working on a book that explains that now, so that'll come out when it does. But anyway, main test driver programs for the first 2 pushbacks. I'm just going to put it up there because so you can see what's going on. We're going to reserve some space, and then we're going to demonstrate that the pushbacks here. We're going to check. I'm just using standard assert to just check that, yes, this is in fact what we expect. Regular test case. And now we're going to look at the third pushback. And here we're going to try it. And on the third pushback, we're expecting that it will throw. So if it doesn't throw, it was a bug. And this is a standard way of checking things that you expect to throw. You expect this to be not good. So you write the code in this way. And we do this all the time for checking contract violations, which we've had since 2004. And what happens with a contract violation when we're checking it is if the contract is violated, it throws a bad contract exception, which we immediately check. And this is only for testing, but this is the kind of thing that we do routinely. And it's all packed up in nice little utilities. So here's a simplified myVector class. And here's the array, here's the capacity, here's the size, here's an implementation of the default constructor. And let's see, what do we got here? Pushback, reserve, and swap. Okay, so we're going to call this noexcept because that's the right thing to do. Now, I'm going to just go through what C++03 does when we do a vector pushback. This might actually be illuminating because it's a nice, cartoon. So we have a main, and this one throws on the 4th copy, not the 3rd, just pointing out. This is the 4th copy because it made the slides nicer. So I have 4th copy on this one. And so here's a vector, and we're going to make the 1st copy when we do the pushback. And so it looks like that. And then we've got 1 copy, and now we do a swap, and now we have this. So that's how we do the first pushback. What does the second pushback look like? We have a vector. We create the thing that we're going to swap from, and then we do the first, and that's the 2nd copy. And we do the 2nd, and that's the 3rd copy. And then we swap, and we're that. Is that your intuitive understanding of how vectors work? Hopefully. And then 3rd pushback, we have a vector, create 4 things. That's the 4th copy, and it blows up. So what happens? Goes away, and we're back to where we were. So we have the strong exception safety guarantee. Does that make sense? Just the whole thing that we were planning to do, it's gone. So we got the same state, everything's working just fine. So now we can do some, look at how we might write the code. We're saying if there's enough capacity, we don't have to worry about anything. And if it throws, what are we going to do, right? There's nothing to do. If it throws, no problem. Because we don't need to grow any more space. We don't need that. Then we say, okay, here's the size we're going to grow by. We're going to say if the next capacity is, if the capacity is at least 1, we're going to double it. Otherwise, we're going to make it 1. So that's what that line does. And then without a noexcept operator, we do this. We have a throwing move. So that may throw, that may throw, that may throw, that may throw. And then now we do the swap. Once we do the swap, it's not going to throw. This is how we write the code. We need a compile time operator to ask the question, are you going to throw? So if we evaluate this expression, may it throw? And what does the magic code look like to do that? So here's where we were before. And now we're gonna put some magic in the if statement to ask the question at compile time, are you going to throw? So let's look at this. So this is what it would do if we were in C++11 instead of what we saw before. So this is the C++11 version of vector, and we create a vector, and we do a pushback, and there's the temp vector, and now the size is 1, and now we have 1 copy. And now we swap. Okay. 2. And we have the vector of temp, and this time we make a copy. That's the second copy, but now we do a move. And we still have 2 copies, and now we do a swap. And we have the third pushback. We have vector temp, and we create again. And this time we have the third copy, and we do a move, and we have 3 copies, and we do a move, and we have 3 copies, and we do a swap, and we have 3 copies, and it worked. So we did less work. You see right there, we did 1 fewer copies, right? We're great. And so this is a good thing. So it's worth doing. It's clearly, if you're dealing with the same memory pool, you're dealing with, happen to be using local arena allocators, and you're using moves within that arena, that's a win. If you're going across arenas, that's a loss. So you have to be mindful about when you're moving and where and why, and if you're doing high performance, multi-threaded, you know, all this good stuff, you need to know when move is actually a good thing and not. That's not really the point of this talk, but I had to say it. So what goes there? Does anybody have an intuition as to what goes there? It's a little more complex than you might think. We'll see. So what goes here? Well, we got to create this temp, it might throw, and then we're going to reserve the capacity. That's a no-throw operation. This is the last thing that might throw. And then, and again, I'm using the old style for loops because quite frankly, they work just fine and everybody understands them. If you want to use a for each, bless you, don't make any mistakes, you can read about it. And then that's a no-throw operation. And then that's a no-throw operation, and that's a no-throw operation, and we're done. So you see, you acquire all the stuff, and then you do what you need to do. Once you get past this point, you're committed, and there's no way the thing can throw. And if it does throw, then it terminates because there's nothing to be done. If you have, okay. So what goes in that yellow box? That's really the thing we're trying to answer here. So this is a hint. That's the thing that can't throw. And it looks like that. Pretty, right? If you try to do something else, you won't get what you think you're getting. And we'll sort of see why that is in a little bit. But just letting you know, this is what you have to do to get a good result. I know this because Alistair Meredith actually wrote this code with me, And Alistair Meredith is very, very crisp on what it is you need to do to get this right. Alistair Meredith is a former library working group chair. He works with me at Bloomberg. So I know this code is right because Alistair said so. Okay, so we can, as I said before, we can enforce, we can use this as a way of saying, I don't cover that at compile time. So imagine we have this little geometric function, and it's going to return the sign. And remember this old one, SOHCAHTOA? Sine opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent, which every school child knows from trigonometry. Anyway, we're implementing this thing, and returns the square root. And I put in the comment that this doesn't throw. It doesn't. It's a fact. It does not throw. I know that, and so I can assert that it doesn't throw. Now it really doesn't throw. I could put noexcept there. Now you can see, not only does it say to the human being it doesn't throw, and it says to the compiler that you can't compile this if it throws, it actually puts something there that you can ask it at compile time if it throws. Why? Why would you ask it at compile time if it can throw? You don't know if it can throw? You just told me it can't throw, and you made sure it won't compile, and now you want to ask if it can throw. The thing is, there's nobody who cares about this that's going to ask if it can throw. And so if somebody has a function that they know won't throw and they put it in here, knowing it won't throw, but it isn't decorated with noexcept, this will be rejected. And my statement is, this is not what noexcept was written for. Noexcept was written for generic code, specifically for move and swap, pretty much. And so I just want you to think about, just because you can use something, do you really want to use it? And my personal belief, because we don't have opinions in this book, but I can tell you my belief is this is not a good use of noexcept. In fact, it's annoying. Anyway, moving on. Doesn't do anything for you. Standard containers have no choice because C++ legacy code, they must provide the strong guarantees support types that might throw if asked to move. Non-standard containers like myvector, they don't need to do that. They could say, we're going to provide the strong guarantee wherever we did before, but if you pass in an object that might throw on a move, we say no, sorry, I can't help you there. And if we do that, we can omit some of the complexity, and we can write a function like this. We just static assert that it can't happen, and then we take care of the case where we don't need any more room, and here's the case where we need to grow it, but we just grow it the old-fashioned way. We don't need to, if we get here, there's not enough space, but the element is no throw anyway, so we just, not the old-fashioned way, we just move it the modern way. We leave out the old-fashioned, we're going to assume that it has the move operation. And so we don't need to ask the question, we just simply assert that it's true. That gets rid of the if-else. Okay. So other cases, there's some other reasons to use this thing. We could use pushback of ref, and that's what we got. So what are the pitfalls? Well, it considers the entire expression. So for example, if you did this, this is a chapter 3 feature conditional thing. Assumes there's an accessible default constructor, and also invoking the destructor is part of the constructor subexpression. So when you do that thing, you're talking about all the operations that follow from constructing something, including the destructor. But that wasn't the question you wanted to ask. So that's why we had to do that really grotesque other thing. So we can get around it by using declval, and declval is one of those other fancy things that I have never used in my life, but you can use it in this way if you do it just right. So this is what we could do instead. Okay. This invokes the destructor. This does not invoke the destructor. You see that little bit of cleverness? Now, I don't know how anybody could be expected to know this stuff. It's just obvious to you, Dietmar, right? Dietmar, it's obvious. For everybody else, you have to do some work. Okay. But he does work, he does this for a living. I mean, he's a veteran here. The noexcept operator doesn't parse the body of the function. The noexcept operator doesn't care what the body of the function is at all, and that's good and that's bad. Just giving you an example. Sometimes you'll get a warning, and sometimes you won't. And it really depends on how complicated your body is. Compilers are allowed to warn when it thinks you're doing something silly, but can't always figure out how silly you are. You can be, foolproof, but not damn foolproof? Anyway. So, object code optimization is another matter we're going to talk about shortly. So how am I doing on time? 36 minutes? Is that correct? If I'm into it? That's it? Geez, we're doing well. We're on slide 131 out of 201. Good news, we don't have time for questions. All right. So, moving on, annoyances. The noexcept operator is too sensitive for direct use, or it actually picks up every nuance, and so sometimes you want to work around it. We have some standard library traits that we can use. For example, no throw assignable, no throw constructible, no throw copy assignable, no throw copy constructible, no throw default constructible, no throw destructible as, yeah, no throw move assignable, and you get the idea. So likely there's something in there for you, and if you use the trait, you don't actually have to use the direct thing. So just ask this question. Okay. The strong safety guarantees itself, probably a bad idea. I think it was an overreach. I don't think any of the work that we spent on this was worth it. We could have done things a lot simpler if we didn't have to keep twisting and doing things to try to keep that alive, but we do. So an alternative is simply if you're doing a large transaction and the thing goes bad, you know, you can just get out of the whole thing. You don't need to worry about the individual objects being having their integrity because you just realized the thing went wrong. What are you going to do? Are you going to somehow fix it in some sort of micro sense, or are you just going to say abort the entire transaction? And if you do want to do it, the copy swap idiom is a good one to use. So there is an interesting change in unspecified behavior, and it is unspecified from C++ 03 to C++ 11. It's worth noting. So if you have a vector of scalar types, like a vector of scalar types like this, and you do a pushback so that the first element is a vector of something, right? And then you reserve in the vector. I reserved space in the first element vector, so I now have 9 integers of the first element of my outer vector. And then I do a pushback. If I do a pushback, it grows, right? It grows, and then it does a swap. You'll notice that the capacity went away. Because when it grew the other one, I didn't do the reserve on it before I did the swap. Notice that? So remember what happened before? We swapped the other one that was created, we had a capacity of 0. So it didn't get reserved. So that happens here. Now if we go over there, look what happens here. In this one, the vector inside moved and the state moved with it. And that's probably what you thought would happen when you wrote this code. Because why on earth would it go to 0? Only if you know how it's implemented. Well, guess what? With move, it does what you think it would do. So this is actually a little improvement, but it's different. And then whenever you make a change, it's annoying, right? Because it's different. So know that. It's not true for vector of string, because it doesn't have that same property where it comes up null and whatever, it literally moves it. So we're good there. It's a slightly different situation. Destructors only are no except by default. Whenever you have an exception, something's a little different. Oh, exception's a pun. Then things are more complicated. So user-provided destructor will default to no except, but a user-provided move operation will not. That's questionable. Was that a good design decision? So if a class like this has bad ideas as a base or member, then it will implicitly have a destructor that is no except. Okay. What else? Oh yes, turns out that early versions of the standard were imprecise or insufficiently explained, and so things didn't behave the way they were supposed to behave. And so you've got some things like this, where if you have, okay, so F0 return 0 const expr, but the second one is not working this way on older versions of GCC and MSNBC, and the same for this one, but it was fixed eventually and over time. So the code is changing. It's now more stable. But this gives you an idea of all of these things should be this way, but as I said, you might find some flaky behavior on older compilers. Okay. And we are finally through the noexcept operator. And now we can dive into the noexcept specifier. So it's a chapter 3 feature, and chapter 3 features are the implicit bias of the book, which say you really need to understand why you're doing this, because if you don't, you might misuse it. And so I want to point out what's going on here. So the short thing is noexcept specifier. The long thing is the noexcept function specification. Okay, so we're saying to a function, we're announcing to the world, I will not throw. And more precisely, we're saying that I will not allow a thrown exception to come out of this interface. Should such a thing happen, I'll kill the program. That's what that means. So, controlling sentence. A function having a noexcept exception specification denotes a programmatically observable, runtime enforced guarantee that no thrown C++ exception will ever escape that function's body. Again, a nice tight sentence that describes what we're talking about. So I'll let that sit in for a second while I grab a sip. Okay. So description. Primary purpose. Denote explicitly whether a function, particularly a move or swap operation, may throw. That's why it was designed. It was designed very hastily right before C++11 was released, because we had this really horrible situation where something could be moving, could get halfway moved, then we realized we have an exception, we have no way to get back. So we needed this. So the possibly conditional noexcept specifier provides precisely the information we need at compile time. For non-generic code, the unconditional form usually suffices. For generic code, or to override an implicit noexcept, the conditional form is required. So what does that mean? So, specifying non-generic function doesn't throw. Here we go. We put noexcept. Now it's noexcept true. Conditional. Okay, so. So here we have a struct, and it's noexcept false. Destructor may throw. That's explicit. That's how we say that the thing is allowed to throw. Because if you didn't say that, it would be implicitly true. Okay. Generic context function. So this is a kind of interesting case. If I know I can handle something without throwing up to some constant number, like 1024, awesome. Then I can say this, and it says it won't throw if that condition is true. Otherwise, it will throw. And that's kind of cool. There's another one that's particularly interesting. Suppose, and this is a general trend, I think, that people see. You can try to enforce correctness at compile time, but human beings know more than the compiler does because human beings are putting together this multi-translation unit program. And what if the thing that you have, you know it won't throw under these circumstances, but it doesn't tell the compiler that it won't throw. So the compiler, not seeing that it doesn't throw, goes through all this extra work that it doesn't need to go through. So if you create a wrapper that lies, it just says to the compiler, I don't throw, even though I could technically throw, but it isn't going to throw, you get something that will run faster and does no harm. Now, of course, if you wrap something and it does throw, it will abort. There are people out there that say, I'd much rather have a slow program abort so that I know why it's slow rather than just keep running along slowly. When I was thinking, well, it doesn't throw, so shouldn't it go faster? So this isn't as evil as it might seem, but what we're really doing is we're just lying to the compiler. We're wrapping something that technically could throw, and then if you put it in something like a standard container, the standard container can optimize it, assuming that the copy won't throw. And most of the time, the copy doesn't throw, right? So it's all good. Stating that a function itself is noexcept if and only if evaluating a given expression is noexcept. So that's the conditional noexcept again. And this is an example of where you want to make a statement that as long as what you give me, whatever your type is, I myself won't do it. And this is repetitive. And there have been suggestions as to how to fix this, and they never seem to get adopted. But whenever you want to express this, you have to do some repetition. And that's an opportunity for mistakes. And yes, we all understand that. The noexcept operator will return false if the invocation of function f is permitted to omit an exception. The const expr function f is invoked at compile time, and the result is implicitly contextually converted to bool. So these don't mean the same thing. One of them is what we intended, and one of them is just ouch. So you need to be careful that you don't accidentally write the wrong thing with the noexcept conditional specifier, because it has to have that double thing in there. Does this make sense? This is kind of a little subtle. Okay. If you violate an exception specification, there's stack unwinding. STD unexpected is invoked. With noexcept, the current stack frames up to the violated function invocation may be unwound. It's different on different compilers. Sometimes the compiler just says, I'm good, and it just gets out. Other times it cleans up the current stack frame. And so this is different on different compilers. But STD terminate must, at the end of this exercise, be called. So here's just some examples of what this looks like. So here we have f, and we say noexcept false equals default, and OK, default constructor. And now we say, here's the copy constructor, and error, copy constructor is deleted. And OK assignment. And we have, right, move, and then we have the destructor. And so this is what we get. And this is how the compiler interprets it. And I wish I could give you some more intuition into this, but I'm just going to let you see it. And these are the facts. Yikes. As of C++20, they said that was a bad idea. They said, you know what? Instead of making people write this code by hand, we're going to allow people to say what it is. So if the compiler thinks one thing and you think something else, you win. You just tell the compiler, look, I know, you don't know, I know. And then you don't have to go through that wrapper stuff anymore. So as of C++20, they decided to do it. There are many reasons why they decided to do it. One was they couldn't implement it the other way. And so effectively. And again, that has to do with something about the ordering in which the compiler does its stuff. But having this thing be stated as fact, not only is it easier to implement, like it can be implemented, but it actually does what you want it to do. It works with you rather than fight you. And so this is a good thing. And sometimes it takes a while for people to work through things, and that's why we need 7 years between when the language comes out and when we talk about what's going on, because we need some experience with it. And so they got some experience and they changed their mind. That's good. So this is what happens now. Oh, sorry, went back a little too fast. So this is the good news. The good news is there are no exceptions. You just get in the plan. You just say what it is, and it is what it is. And if you get it wrong, it's on you. But at least it doesn't fight with you. At least you don't have to go and write something by hand to really argue with the compiler. You can just tell the compiler, no, I mean this. All right. And by the way, if you're not sure if it is or isn't, you can always just write a little static assert while you're developing your code to say, is it noexcept? And it'll just tell you, yeah, I'm noexcept. Okay, great. Now I'm going to put the little label on that says you really are this, and it's all, I'm just making it explicit, but anyway. So this is just explaining how we do assignment of functions that carry the noexcept, because it became part of the type system. And so this is before it became part of the type system, it still tried to do the right thing. And so you can imagine that you can have something that's, you can assign something that doesn't throw to something that's allowed to throw, but not vice versa. That just makes sense. And again here. And virtual functions, it's the same thing, same idea. You can't have something in the base class that doesn't throw and something in the derived class that does throw. It's the intuitive. You have a stricter, you have wider preconditions in the derived class than you do in the base class. You have stricter postconditions in the derived class than you do in the base class. That's that whole thing. It's not always true that that's the right thing to do, because if you have global knowledge and you want to have something here that doesn't satisfy that requirement in general, but does satisfy that requirement for a particular instance, that can be a good thing, which I'll talk about a little more in a moment. So here's an example. It has the constraints apply to defaulted virtual functions, most notably destructors. So yes, in short, a virtual function can throw only a subset of what can be thrown in each base class. That's just intuitive, I suppose. Can be annoying though, as I said. All right. Explicitly declaring a destructor noexcept false. So this is not a good idea. It's really not how we write code, and quite frankly, if anybody is ever writing a destructor that can throw whatever, you know. Anyway, if in the process of doing stuff and a destructor and an exception is thrown and all craziness breaks loose and then terminate is called, and it's fine. So, use cases. So, despite all the complaining I have about Chapter 3 features, all Chapter 3 features, almost all of them, have some redeeming social value. And so, if you use them properly, they're good. Better algorithms. So, if you're dealing with the strong guarantee and move, then you really, really want to use this. You want to specify that this move is noexcept. That's a great thing. Love it. You can suppress exception handling code, and that means the code size will go down typically when you do this. And the third one, better runtime optimized object code. This is all but a myth, turns out. People say it, but you have to work very hard to demonstrate it consistently. In other words, in most cases, it'll have no effect. And in those very specific cases where you engineer it to have an effect, the effect will be negligible. Just saying. But if you put exceptions all over your code and you like exceptions, they're your friends, they won't work very well because as soon as you hit a noexcept function, boom. So you might want to think about this. So anyway, really good, right? This is good. Low cost, high reward. And these are high cost, low reward. That's why they're chapter 2 and chapter 3 features. By the way, chapter 2 features can be really good. I'm not saying that they can't have a high reward, but they do have a cost, and you need to know what you're doing. All right, declaring no-throw move operations, part 1, non-generic types. Is there some benefit to declaring a move operation? Typically when there's resource allocation. So if I know that there isn't going to be any allocation and I'm asking the question, in other words, there has to be some generic code out there that actually cares and is going to switch, is going to fork based on whether this thing does or doesn't throw, then that's the time that you really want to know if it's going to be noexcept. But if there's no question out there being asked, then there's no point to the noexcept, except maybe to reduce code size. So here's an example. We have a vector and we have normal stuff, and we say this is noexcept. So yeah, this trait will give us what we want to know. Okay, and similarly here. So we could do this. No-throw swap is very important because sometimes you can't have a no-throw constructor, but you can have a no-throw swap, as Pablo pointed out to me while he was designing some of the examples for, I think it was even this feature, wasn't it, Pablo? I think you were working on this thing, yes. So Pablo was helping me. He's one of the many people that worked on the book very aggressively. And it turns out that if you are not in a situation where there's a no resource allocated state, if that doesn't exist, in other words, no, what do they call it, radioactive state sometimes, or a partially constructed state, then you might not be able to have a no-throw move or copy, but you could have a no-throw swap. So this is an interesting situation, and swaps are generally expected to be noexcept. So this is what we talked about. Suppose we know either that a move operation can't throw or won't. If it does, the only thing we want to do is terminate. I was talking about this before. Then all you need to do, why should we copy if we can move? And if it blows up, oh well. So here's the noexcept wrapper, and it just looks like this. And it turns out that we have to, over here, until C++20, we have to implement the functions ourselves. But once we're in C++20, we can just say that they are in fact noexcept true when they're not, and life is good. So anyway, so it is true, admittedly, that we can reduce object code size. Less code runs faster, right? Well, that's a good rule in general, but not in this case. On medium to large computers, almost the overall program size, the size of the executable itself, does not affect runtime performance. What affects the runtime performance is what is in cache. And if you get any exception code in your cache, that will slow things down. However, that doesn't happen because the noexcept, the exception technique that's used is deliberately designed to make throwing an exception ridiculously expensive and not throwing an exception free. And we really do mean free. There is no overhead. No overhead, not a little, no overhead to that. Now, there are cases where stack unwinding will produce a tiny little bit of overhead, but that's not the exception itself. And I'm going to try my best to explain this and give you some data. Reducing object code size. Well, when the exception is thrown, the destructors of all non-trivially destructible live objects in the current stack frame must be invoked. Okay, so this is what happens. I've used GG and FF consistently throughout, where F is calling G. And when you have a function F and G, and we've got this function F and GG is here, and GG is call number 0, there's no object code overhead here. when we have the second call after a variable that has a non-trivial destructor, there's some code overhead. If we do another one, and then there's some more overhead. So you see, not all things even give you overhead. You have to get to the point where you know that there's overhead. So there is overhead here. Now, if we put no except, no object code overhead, no object code overhead, and no object code overhead, because there's nothing to clean up. Does that make sense? You see what I'm saying there? This is giving this thing permission to just go, I don't have to clean up because you told me there's nothing in here that throws, so I'm good. All right. Now, if we make that no except, no object code overhead, no object code overhead, no object code overhead, because F knows that everything that it's called inside there doesn't throw. So since it doesn't throw, it doesn't need to put anything to check it. All good. But if we say no except here, and we don't say no except on GG, some overhead. Oops. Some more overhead. Oops. Some more overhead. So by putting the no except on FF, we actually increase object code size. Does it make sense why that would be the case? You see that it's like we're putting an additional thing. We're saying we will not throw, which means I got guys in here that are throwing, so I better check to make sure that if they throw, I call terminate. Okay. So that's just an interesting fact. It's not always true that it reduces size, but typically it doesn't increase it by much, and sometimes it reduces it by a fair amount. But you should know what you're doing, always. Now, what's interesting is, if you have a function body and it's inline, or it's a template, the compiler can look inside the function body, not to ask a question about functionality. It can ask the question, the way it's implemented today, do I have anything to worry about? No, and it can optimize that away. Some people use noexcept to allow cross-translation unit optimization. Huge mistake. What we need is something better than that, and I'll explain that in just a minute. So, the function FF contains one or more automatic variables, non-trivial destructible type S, otherwise there's no destructor invoke, okay? There is at least one expression in the body of function GG that might throw, e.g. invoking the noexcept false function. Otherwise, there's no need for logic unwinding logic. That's it. Now, if the potentially throwing function is invoked while one of those variables is alive, then it needs to be cleaned up. Otherwise, there's, again, no reason to do it. So if you had a little internal block, you then call the function. If the thing's already destroyed, nothing to do. Okay. Tiny benchmark. So here's a struct, here's a G function, here's what's about to be a table, here's an F function that calls G with the struct afterwards, okay? It's after, so we call G, G's done, now we're gonna create a S. So S lifetime begins after G is called. So here's a benchmark. 88, 84 means 88 optimized, 84 means not optimized. That's with no except off of both. The second two are with G no except, the second and third are with G no except, the third and fourth are with F no except. So the third one is with both no except. You'll notice that the first three are the same, but when F is no except and G isn't no except, it gets bigger. You see that? This is just a little teeny, just to give you an idea. Now, and I'm explaining what that means. Now if we add another one where we reverse it, that's all I did is I just reversed the two. Now, look, big cost. In the case where you don't do either, big cost. But if you do both, it's still the same. So just inhale this. Like, just know that this is the truth. I would not lie to you. Okay. I'm particularly proud of this slide, but unfortunately those things are reversed in the book in the first edition. I'm so sad. But they're fixed in the next printing, which I hope is coming out after we get all of the glossary terms, right? The book has all the glossary terms in the book are, first time they're highlighted in a different font in bold, and then every other time they appear in context that mean what the glossary term says, because we're going over word by word. It's horrific. They're in the same, they're not bold, but they're still in a different font, and it looks like somebody has kidnapped somebody and they're giving a ransom note. It's unfortunate, but oh well. Anyway, that's what it looks like. But it's useful. We're engineers. We put up with a little annoyance sometimes. So these are exception specifications, G under S and F under S. They're just so they're macros, so I can turn them on and off and do test cases. All right. Pitfalls. So overly strong contract guarantee. What is a contract? Right? A contract is between human beings. It's a transaction. You know, in a transactional agreement, if you give me X, I will do Y. That's a contract. Right? It's got a precondition. It's got a postcondition. Sometimes it has some essential behavior involved. This is how we document our stuff. But this is for human beings. Narrow contract has preconditions, a wide one doesn't. If you give me X, I will do Y. But if you give me something other than X, I will do whatever I want. You may hate it. That's okay. That's a narrow contract, right? If you do this, I'll do that. What if you do that? Well, I don't know. We didn't talk about it. Well, there's no contract. Now, here's a double square root. Return the positive square root of the specified value. That's a contract. What happens if it's, well, this is actually wrong. Return the non-negative square root of the specified value. I can't believe I actually let that in. That is a true bug because 0 was included. This happens all the time. Whenever you hear positive, think non-negative and then write it because that's what it is. Okay, the behavior is undefined unless value is non-negative. So now here there's you see what I'm saying? That's not consistent. It should be return the non-negative. Well, you know what? I take it back. The positive square root, meaning not the negative square root, but you know what I'm saying. It's a little disturbing. Anyway, the behavior is undefined unless value is non-negative. Also, I have jet lag. I just came over yesterday, so. All right, so this tells you what isn't in the contract. Now, if it's not in the contract, I can change it. The benefits of not specifying behavior and negative input. Okay, I don't have to document it, test it, debug it. It's not there. It's good. I do have to test that the contract check it, but so be it. We leave that open for different behaviors later, like in a test build or debug build, whatever we want to do. We make it build mode dependent. That's really useful. Then you can catch bugs. But if you say what happens with, let's say I decided, well, if it's negative, I'll just take the absolute value. No. Now you're saying somebody passes in negative 47 by accident. You're saying, oh, that's fine. I'm sure they meant 47. No. We keep open the option of expanding the domain and still preserve backward compatibility. So with the thing that happened with vector, where that thing changed from being reset to not being reset, that was not backward compatible. It might be better, but it wasn't backward compatible. It would have been better if that was unspecified completely. In other words, that there was like explicitly stated that you cannot rely on the capacity of a vector and a vector, but it doesn't say that anywhere, it just is. So that's kind of in the middle. It's in that gray region. Overly strong contract guarantee example. I have a business sort. Modify the range of the contiguous double values between beginning at the specified start address and extending n elements so that it is sorted in ascending order in time that is order n log n. If this sort routine is being used once, that might make sense. But what if the sort routine is being used billions of times a day and what you're looking for is aggregate throughput? So this would eliminate quicksort. This is an overly restrictive contract. You don't put that in unless you mean business. And if you do that, you restrict the implementation choices. Similarly to that, noexcept restricts what you can do. And you're promising now and forever that any piece of code ever written anywhere can look at this thing and will see this does not throw. And that means that it will make decisions based on your promise that it will not throw. You can never take that back. What if sometimes it doesn't throw because it doesn't throw, and sometimes it throws because that's better? Wouldn't it be nice if you had something other than a promise to give people. You say, I'll tell you what, if we were in the same translation unit, you could see it doesn't throw. I'm going to put a little hint on that says, oh, and by the way, today, it doesn't throw. And then the noexcept operator wouldn't be able to operate on it because it's just a hint. But the compiler knows it's not really just a hint, it's really true. And so the compiler can optimize the code and not create the code bloat. This would be nice. So what I'm saying is, instead of having noexcept with its full force of contract, you had something less than the full force of the contract, but still good enough to do the optimization. Now you get everything. You get any kind of speed up you could get. You get all the code elision you want. It's all good. But we don't have that. But please think we need it. But we'll get there. So that's what I'm saying. It's a promise and it's irrevocable. So noexcept, you can put it on. Once you put it on, you can't take it back without breaking potential clients. So that's my passion speech here. Now, conflating noexcept with nofail. Noexcept doesn't handle or suppress exceptions. So if you put noexcept on something, that doesn't change anything. It just is telling people down the road that I promise that I will abort this program, terminate the program, in case an exception gets to me. Big whoop, okay. There are definitely places where no-fail functions make sense, but we want to say that in the contract. This function, it's not that it's noexcept, it will work. You can count on its working. And really the only thing that could possibly go wrong is your stack frame, for example, hits the top of memory or something, in which case, oh well. But it's not the kind of thing where you could dynamically allocate memory and it would throw an exception. You wouldn't have some object that might throw and it'll just die. This function, like square root, is a no-fail function, right? It just doesn't fail. There's no reason for it to fail. It's got all the resources it needs to succeed. Obviously, again, if the computer catches fire, if it's hit by a bomb, function will fail. But within reason, it's not going to fail. Vector pushback isn't no-fail. Okay. Vector at isn't no-fail either. What does vector at say? If I call something out of contract, it's going to do something. What's it going to do? It's going to throw an exception. That requires resources, potentially. All right. Other pitfalls, accidental terminate. So if you use exceptions all over the place, what could happen? Forgetting to use the noexcept operator, imprecise expression with the noexcept operator. What if you just don't get it right? Then either you get unnecessarily poor performance or you get an unexpected program termination. Noexcept is a funny thing. You really need to be mindful. And as I said, the benefits of it are very, very small in the right, they're huge in the right place and very small, if any, in every other place. And in some cases, costly. Runtime performance, that's the holy grail. Everybody says, oh, it'll run so much faster. I defy anybody to demonstrate that. Benchmarks exist. You can find it, but there's so much noise that you could just, for example, increase your code by one line and it could run faster just because of boundary conditions, cache things, just the way the code aligns. It's remarkable how a little change in code can have a tremendous speed up or speed down, if you will. We use the zero cost exception model. And again, Pablo and I hashed this out for a long time. What exactly is it? What's going on? Whatever. And it really, literally doesn't have any cost. Really doesn't have any cost. Adding noexcept where there's no theoretical basis for improvement simply randomizes performance. So, even where it's possible for noexcept to speed something up, it's still little. It's like one instruction in practice. So it really happens in a context where because this thing was written in a way where it typically would handle something that throws, like a shared pointer or something, and you happen to know that this particular thing won't throw, the compiler can take one instruction away. It can actually optimize one load instruction. Big deal. I mean, and I'm saying that, I care about performance very much. But when it's barely measurable, like have to really put it under the microscope, this is not the kind of thing we want to torture the entire population of programmers in the world, putting no except everywhere and incurring all the wrath that that causes with people who realize that that's not a good idea. Anyway, the only thing we care about is the hot path. That's the only thing we care about. And if you look at the hot path, the instruction stream and what's going into the CPU, that stream of instructions, that's all that matters. And so there is a lightning talk that describes this, C++ on the C 2019 by Niels Decker. So if you want to hear another statement of this, he also has a whole library of things where he's benchmarking this and demonstrating what's going on. So I'm not the only one. But we created this micro benchmark with unique pointer. And I just want to show you what's going on here. Object size on the left, runtime on the right. So object size, runtime. And just this morning, before I took my 50-minute nap before this talk, I looked at picked something to just compare the difference. Notice how much the size is smaller than 1. Now look over there. I looked at both optimize for speed and optimize for space on Microsoft. And I didn't cherry pick this. I just tried to pick something that sort of goes against your intuition. The size goes down, but the speed, well, the performance goes, the size gets better, but the performance gets worse. Do you see what I'm saying? When you go from the one line to the next. And this is giving more and more reason for there to be a problem. In other words, this going down, I've got in the function that I'm calling, there are more and more instances where I can optimize that one instruction away. But there's so much noise that good luck finding it. You see what I'm saying? Now, this actually does have a performance benefit. Buried in those numbers, if you add them all up, there's a tiny little average performance benefit, but it's not significant. This is significant. So if what you really want to do is make your object code size smaller for whatever reason, then you have some data. But if you want to make your function faster, benchmark it. You'll find out that if you just change the instructions around a little bit, it'll get faster. You keep that one, because that'll make more of a difference than the noexcept. So, annoyances. So, first one is optimization conflated with code size. Virtually all runtime optimization is algorithmic. Anything that you could possibly get from just a peephole optimization in terms of performance is negligible. Algorithms are contractual. Object code optimization is not contractual. So it's as if I'm saying, I'm going to put this code is optimized as a compiler flag, and unless your code is optimized, you can't call me. It's that kind of thing. It's incompatibility that's just horrible. The compiler's allowed to optimize code without there being a promise, as long as the compiler knows that that's okay. Templates and inline functions, for example. So I propose this does not throw attribute, and it's just like noexcept, but no promises. And the compiler can count on it in another translation unit, and you get all the optimization you want. But if I call noexcept on this function, unlike this one, this returns noexcept true. This one returns noexcept false. And so anybody who's writing code that's based on whether this thing can throw hard code, that code will take the slower path because we're not promising forever and always that this is going to be true. And that's really a good thing, because I'd love to give you the optimization if I don't have to give it to you forever. And then no one would have a problem putting this on, because I wouldn't have a problem. I'm just saying you're just doing what you would do if you were in the same translation unit. So that's a good thing. So this is a good idea. Anyway, other annoyances. Code duplication, expression aliases could help. Noexcept is part of the functions type, is not part of the functions type until 17. And ABI changes in the future could happen, and that would be, a drag. Exception specifications do not trigger SVN, and this is where Alistair's abilities exceed mine sufficiently that I'm not going to dwell on it. It doesn't participate in overload resolution. I don't know if that's a good thing or a bad thing, but it doesn't. this is another thing that annoys me, because there are cases where I know I can derive something, and even though it doesn't satisfy the letter of the algebra that the compiler understands, I know it works, and I want to do it, and the compiler won't let me. And if my alternative is just to make everything a void star so that I can bypass the compiler's annoyance, you know. So the compiler let me in C++20, it let me say the thing wasn't, was no except when it wasn't. Could it at least let me say, yes, this thing derives from that thing, and I know it isn't, but I still want to do it anyway. Could you not stop me from doing it? But that's not the way it is. Anyway. So this is basically the constraint. And I think I've just got an example here. This is what I want to do, and that won't compile. I want to do this, but it won't compile. All right, why doesn't it compile? Well, again, this is people being what Strustrup said in his Evolutions of C++, excessive nannyism, I think. Anyway, not about this. He said it about when he didn't provide overloading the question mark colon operator, I think, or some other such thing. Always try to find that reference. Anyway, so we're at the conclusion. I haven't gone over my time. Amazing. All right. Takeaways. Noexcept was invented to solve a problem that occurred because a contract promised too much. That's one takeaway. Don't promise too much in contracts. It's typically used on move and swap. If you're using it on move and swap, you're in a good space. You go beyond that, it's used to decorate move and swap operations. That's about it. So the operator is used to ask questions about move operations and swap operations. And the specifier is used to announce to the operator things about move and swap operations. That's it. Anything else? I just want you to understand. That's why this is a chapter 2 feature. Very important to ask the question. If you don't throw, oh, well, then I'll do this other thing. That's fine if you're really asking the question. But putting this all over on everything that doesn't throw just because it doesn't throw is infuriating. It's galling. So. But it is effective for algorithmic optimizations. And as I said, if we didn't have them, we'd be in a bad way. So I'm disparaging them for their misuse, but not for their proper use. And with that said, that's this book, which I will hold up again. And if you want to get it, I would appreciate it. And I want you to read about noexcept, because there's a lot more to noexcept in this book than I did. There's something like over 100 pages on noexcept. Now, what's interesting is chapter 1, surprisingly, is much smaller than chapters 2 and 3, even though it has a lot more stuff in it. I wonder why. Because chapter 1, there's not that much to say. Here's what it is. Here's how to use it. Have a party. Chapter 2, well, you know, and chapter 3, oh my God. So the nice thing is you don't have to read chapter 3 right away. If you're not interested in digging a hole and getting to the end, digging and digging, you just start with chapter 1. But with that said, this is what the advantages are. I'll let you read it. See if that interests you. If there's anything in there that sounds like it might help you, then you know what to do. And this is Vittorio. He's the co-author of the book. So Vittorio, everybody, that's my co-author right there. This book.
Anyway.
And he's only 16 years old. He's actually older, but when I started, when I met him, you were about 17, weren't you?
Yeah, that was a long time ago.
You haven't aged a bit.
CPPCon 2014, I think.
Yeah.
It was a long time ago. Awesome. Anyway, I wanted to ask you, how would you feel if throwing from a function which is decorated with noexcept would actually be undefined behavior? Because I feel like that opens up a lot of opportunities for optimization, but it also, you know, as a whole.
Okay, so you're asking a question that was heavily debated when it was coming out. And at the time, I was so irritated with exceptions because I saw absolutely no reason to have them that I didn't even spend enough time. And Alistair was there at the meeting. It was in Pittsburgh. And this is where the famous, the whole thing was being discussed. And it was about 2009, I think. People were talking about what should happen. And people like Bjorn Strustrup and people in the security and whatever felt that it was just too freaking dangerous to have an exception just flow through the ether with nobody knowing what's going on. And so even though Dave Abrahams, Alistair, and if I had had a vote, but I wasn't there, me, would have agreed with you. But there were people that just, it can't happen. So we're paying a little overhead for the security of knowing that it's something that says it doesn't throw, really doesn't throw, and there's a runtime check. Hey, guess what? Contracts that are checked have a runtime cost. This is an irrevocable contract check. And that's what they decided. And your point is absolutely well taken. And there are plenty of people that agree with you. Just saying. Good people, you know? I mean, Dave Abrahams is like an opinionated guy, and he was like all about it. He was actually very, very disappointed in that choice. Excellent question.
There was a section on noexcept false destructors. If they are marked noexcept false, but they still call standard terminate when you throw within them, why are you allowed to mark a destructor as noexcept false, or what is the consequence of doing that?
Okay, so here's the idea. Before C++ 20, you weren't allowed to do that. It would just tell you you're wrong. But there was a problem implementing that because of the way the compiler does its thing, if I recall correctly. They decided they needed to fix it because they couldn't really implement their implementation experience. But then they said, hey, if you're a smart guy, and let's say you have something like this in there. It says, if hell freezes over, throw. Hell freezes over is a global variable that is set to 0 and it's const. Now, the compiler doesn't, whatever. Now, suppose it's not const, it's in a different translation unit, but it's initialized, it's really const. And you say, if hell freezes over, I want the thing to terminate, right? You see what I'm saying? So not in that case, but in general, what we're saying is, if you have something that programmatically could throw, but in practice doesn't throw, let's say unless you're out of memory, and when you're out of memory, it's fine to terminate because there's nothing else to do anyway, then all the time you're not terminating, you're running faster. And that's the reason. And I think it's a good decision. Make sense? Yeah. Okay.